Okay, folks, let's jump into chapter 2. This is basic chemistry. We're going to talk about atoms, molecules, isotopes. I will include a longer video that I've recorded for one of my other classes, and that PowerPoint. I think it might be because I go through the things slower. It might be easier to follow because there's a lot of stuff. I know you're like, but I'm here for human biology. I'm not here for chemistry. Yeah, but the thing is, to understand biology, you need to understand a little chemistry. If you want to really understand chemistry, you need to do a little bit of physics. It's like every field has a foundation, and you need to know a little bit of what's underneath it in order to grasp this. Now, we're not going down to the level of physics, so a little smattering at the beginning of chemistry, that's not too bad, just a little pinch of chemistry. Anyway, so we're going to talk about atoms, elements, structure of an atom. We're going to use the Bohr model and talk about the difference in isotopes and ions. People confuse those because they both begin with an I. They're drastically different. Isotopes are atoms that have different weights, so the same kind of atom because they have the same number of protons, but they have different weights because their neutrons vary. And ions are atoms that have different than normal or neutral numbers of electrons. They gain or lose electrons, and that gives them a charge, because normally the protons and the electrons, the protons are positively charged, electrons are negatively charged. Normally they balance out, but there are atoms that will gain or lose electrons, and that'll shift the balance, and things will get more positive or more negative because of how many electrons they have. Anyway, let's move on. So basic definitions: matter is anything that has mass and takes up space. Elements are basic building blocks of matter that we can't break down through chemical means. Yeah, I know you can split the atom and all that and nuclear energy, but that's not what we're talking about. More than 90% of the human body is carbon, hydrogen, oxygen, and nitrogen. If you want to add 2 more to that and get up to 96%, it would be sulfur and phosphorus. DNA has phosphorus in it, a lot of phosphorus. So the backbone of a DNA is sugar, phosphate, sugar, phosphate, sugar, phosphate. And so those phosphates have phosphorus in them. I mean, not that we don't use it elsewhere, but that's why one of the places we use a lot. All right, so let's move on. This says a portion of the periodic table, and that's nice. What they are doing right there is doing a they're skipping the middle. Okay, the reason they're skipping the middle is because things in the middle are weird because they have electrons that jump between shells. So let me pause this for a second and pull up a different periodic table. We'll come back to this. Okay, folks, I'm back. What I have here is a full periodic table. They might see I added some happy faces and angry faces too and stuff, but we'll get to that. Things I want to go over first, though, I want to explain that each column is called a period, and each period has chemicals that act the same. They have similar behavior. And when they were first laying out the periodic table, I shouldn't say they, other people were trying, but it was Mendeleev who pulled it off. And I have a video in the links below that'll help you with, or it talks about the history of the periodic table. It's worth watching. It's the crash course video from Mendeleev. But I'm also going to put in a video on, the alkali metals video from Brainiac. And that video does a good job of explaining how all the things in this first column have a similar property. They react violently with water. But all the things in the first column have the same property. All things in the second column have similar properties. And I want you to, and then we have this indented pressed down area in the middle that we're not talking about. And I already told you, that's because electrons jump between layers and it makes things messy. You will hear that when you talk to a chemistry class. Now, then over here, the column with boron on the top, all those things are similar. The column with carbon on the top, all those things are similar. I want you to notice the little number at the top, the 1A, the 2A, at the top of those columns. Over here where, so we have 1A and 2A, and then we have a bunch of stuff we don't talk about, and then it comes back up 3A, 4A, 5A, 6A, 7A, 8A. Those are the numbers of electrons in the outer layer. We'll talk more about that. That's called a valence layer. We'll talk more about it later. But I want you to understand that when they were first making a periodic table, they lined things up that acted the same. They didn't know anything about the structure of the atom at the time, but they lined things up that acted the same. We now know that the things in this column that act the same, the things in the next column that act the same, they act the same because they have the same number of electrons in the outer layer. All right, I'm gonna leave this PowerPoint so I can get to it in a hurry. I'm gonna pause and go back to the textbook. This is from the other PowerPoint that I said I'd give you access to. The one that's a little slower and longer, that video and that PowerPoint, that I think might make it easier to digest if you have the time. Anyway, here I'm pausing. And we are back to the Stubbe abbreviated periodic table that they were working with. What they wanted you to notice were the atomic number, that is the number of protons, okay? So we now know this is the number of protons. Hydrogen has 1 proton. Now there are different weights of hydrogen, but those don't change the number of protons. That's based on a difference in the number of neutrons, all right? Hydrogen always has 1 proton. If it doesn't, if an atom has more than 1, it's a different element. It's not hydrogen anymore. If it has 2 protons, it's helium. If it has 3 protons, it's lithium. I'm so happy. Sorry, Nirvana song. Anyway, if it has 3 protons, it's lithium. If it has 4 protons, it's a beryllium. If it has 5 protons, it's a boron, and 6, it's a carbon. You can see what I'm talking about. The number of protons is the number, is the atomic number. It is what something is. All right, so we've got that. The atomic number, we just explained, number of protons. The atomic symbol, that is the symbol that we use in chemistry, the abbreviation we use in chemistry to talk about this type of element. And some of these are pretty straightforward, like H for hydrogen or Li for lithium. You're like, oh yeah, of course. But gold is AU. You're like, huh? That's because in other languages, oros would be gold, okay? Or stenos for tin, SN. Anyway, so understand that a lot of these are straightforward, but some of them are a little different. The other thing I want to point out, these ones that have 8 in their outer layer, 8 in their valence layer, super stable, super happy, don't want to react with anything at all. They're like, I don't need electrons, I've got all the electrons I want, just leave me alone. All right, moving on. So an atom is the smallest unit of an element that still has all the properties and acts like the rest of that element acts. And atoms are joined together to form molecules. So we will talk about that. Well, sorry. The reason I paused is there's a dog in the way. Anyway, uh, why, thank you. Okay, so atoms, we're okay, just leave them. So atoms join together to form molecules. I want you to know that molecules have covalent, stop pushing, that was the dog. Stop, molecules are made with covalent bonds, okay? Usually, most books at this point we talk about atoms are joined into compounds. And we have either molecules, which are made with covalent bonds, or salts, which are made with ionic bonds. But anyway, we're just going to move on with their definition. So the parts of an atom, we have protons, neutrons, and electrons. The protons and neutrons are in the middle. The P in proton should remind you that it is positively charged. The neutral part of the neutron name should remind you it is neutral. It doesn't have a charge. It has weight, but no charge. And then the electrons whiz around the outside. So protons and neutrons in the nucleus. Outside of that, whizzing around, we have electrons, and they are negatively charged. And most atoms start out with an equal number of protons and electrons, so the atom is neutral. Neutrons, like I said, no charge, but weight. Electrons are the opposite in that they have a charge, and we pretend they don't have a weight. In reality, they have a really, 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 really tiny amount of weight, so small that we can effectively ignore it. Anyway, moving on. So here we have some drawings of elements, and there we have hydrogen when its nucleus is nothing but one proton. Now, this is the normal hydrogen. This is the most common form of hydrogen. If you might have heard nuclear reactor people talk about heavy hydrogen. That would mean that it's not just one proton, it also has a neutron there, okay? And we even have a special name for that type of heavy hydrogen. It's deuterium, like duo, like it's got two things in the middle. There's even a heavier form of hydrogen that they call tritium, which has one proton and two neutrons. But the electron whizzes around the outside, and it's balanced. You got one proton, so you got one electron. You can see it right there. Okay, now carbon, you can see carbon has 6 protons and 6 neutrons. Again, they're drawing the most common form of carbon. That's carbon-12. It weighs 12 because it has 6 protons, 6 neutrons. We ignore the weight of the electrons. All right. And are there other forms of carbon? Yeah, you've probably heard of carbon-13, carbon-14, like carbon-14 dating. Those still have 6 protons because carbon always has 6 protons. You cannot change the number of protons without changing what the atom is, okay? So they have 6 protons, but some atoms of carbon are like the one drawn, and they have 12 for the total in the middle, 12 in the nucleus, which means they have 6 neutrons. Some have 7 neutrons. So these two atoms would both be carbon because this atom has 6 protons and this atom has 6 protons, but they're different isotopes, different weights, and that can give them different properties. Certain isotopes could be radioactive, for instance, like carbon-14. All right, nitrogen, you can see, and while we're talking carbon, notice that there are 6 electrons around the outside, but they're arranged in shells, like layers, okay? Layers like in an onion. When you cut through an onion, you see a ring and a ring and a ring and a ring inside. Okay, so we have a nucleus in the middle, and then we have a layer around it that can hold a maximum of 2 electrons. That's true not just for carbon, you see a nitrogen, oxygen. That's true in chemistry in general. The inner layer can hold a maximum of 2 electrons. The next one can hold 8, okay? So if you look, you're like, well, we have 6 protons, and to balance the 6 protons, we got 6 electrons, and we put 2 in the inner layer. So the outer layer has to have 4, because 2 plus 4 is 6. Okay, great. So the outer layer has 4, but that's super important. You might have heard that all the life we know of is based on carbon, that humans are a carbon-based life form. Carbon wants to make 4 bonds. The reason why is because all the atoms want to get to that period on the periodic table with 8 at the top. Remember I showed you Roman numeral 8 at the top? And I said those are super happy, super stable, because they have the number of electrons that makes them happy. 8. All atoms want to have 8. Okay. So if you look, carbon's got 4 in that outer layer. Valence layer 4. Carbon wants 8. So that means carbon wants to borrow or share until it can get to 8. That means carbon will want to make 4 bonds. Anyway, moving on. So nitrogen, you can see it has 5 in its outer layer. It wants to get to 8. So nitrogen can make 3 bonds. Oxygen, it has 6 in the outer layer. It wants to get to 8. That means it's missing 2. It's 2 away from being in that happy place. So it has the ability to make 2 covalent bonds. All right, let's move on. All right, the atomic number is the number of protons, and it's different for every element, but all the atoms in that element have the same number of protons. That is the atomic number for that element. The mass number is what you get when you add up the protons and the neutrons, okay? And each proton has 1 atomic mass unit. Each neutron has 1 atomic mass unit. Electrons, we ignore. There is a little mass, but it's so minor that we just ignore it, okay? So don't be freaked out about that. And atomic mass, when people say atomic mass, it's the average atomic mass unit for all the isotopes of that atom. So let's see if the next page has, no, it doesn't. So I'm going to give you some examples from that other PowerPoint. Hold on a sec while I pause. Okay, this is a slide from the other chemistry PowerPoint. And you can see, if you look right here, it has iron. Iron is atomic number 26. So you know that iron has 26 protons. Straight out simple. The average mass for an iron atom is 55.845. Now that's not a whole number. That's a decimal. It's the reason why is it's an average. Because you either have a neutron or you don't. It's not a fractional thing. All right. So when you look at this, if iron for its atomic mass unit, for its atomic mass, has 55.845, what that tells you is that most of the time, iron has 56. But there are other possible numbers. And those numbers are because some atoms have more neutrons, some have less. Now, let's take this, that little bit of information, and look below here. Okay, we see that there are iron 56, which we would expect, but there's also iron 54, 56, 57, 58. All right, so there are different types of iron that weigh different amounts because they have different numbers of neutrons. We get that. But now, look at the mass of an individual isotope. The one that says the one we call iron 56, I told you that's going to be the most common. How do we know that? Because when you round to the nearest number, 55.845 is really close to 56. 56 is going to be the most common isotope. So now we look, and sure enough, iron 56, that's more than 90% of all the iron atoms, okay? Real straightforward. Iron 56 is 91, almost 92% of all iron. Are there other forms? Sure. There's an iron 54 that makes up less than 6% of the iron we see. There's a iron 57 that makes up less than 2%. There's an iron 58 which makes up less than half of 1%, closer to 1/4 of 1% of iron. But you got different forms of iron, different isotopes. Remember, an isotope is just a version of the atom that has a certain weight. And the reason this isotope is different from that isotope, they're the same elements, they got the same number of protons, but these two atoms have different numbers of neutrons. Good? All right. Let's go back to the PowerPoint for your book. Okay. So we've said all this stuff before, but let's go over it. The atomic number is the number of protons. It's different. The number of protons is different for every element. The mass number is the sum of the protons of the neutrons. The atomic mass is the average mass number, okay? The average weight of the different isotopes. That's annoying me. See if we can make this come back. Yeah. Excellent. All right. So we should be recording. We should have the periodic table here. Let's move on. Isotopes are atoms with they're the same element because they got the same number of protons, but they have different numbers of neutrons. And that gives them a different atomic mass. Yeah, you've got that. Radioisotopes are isotopes that happen to be, they're real unstable, and they like to fall apart, and they give off radiation. That could damage cells, it could cause cancer, it could also be used to kill cancerous cells. Useful for imaging the body, for killing bacteria and food, sterilizing. Oh, and there they say killing cancer cells. Let's move on. So, isotopes. If someone has thyroid problems, you can detect the thyroid cancer, say, using radioisotopes. Or here, they are looking at the brain and the function of the brain. So we use this stuff, we use radioisotopes in medicine all the time. All right, so molecules are atoms that can be hooked together, or are made of atoms that are hooked together. They can be the same or different, like O2, you got two oxygens. They're the same. H2O, you got two different kinds of things. You have two hydrogens and one oxygen, okay? So if something is a compound, all right, here's the book definition they're using. If something is a compound, the molecules are made out of different things. So oxygen, O2, molecule but not chemical compound, using their definition. All right, two types of bonds can join things together. There are actually more bonds than this, but the two they're giving you, the ionic bond, the covalent bond, those are the strong bonds. There are also weak bonds that are important. Things like van der Waals bonds or hydrogen bonds are considered to be weak bonds. And yes, we will get into those things later. All right, let's move on. Okay, I had paused and queued up some of the videos that in a face-to-face class I would have paused and shown to students. You can see them, they're below, might be interested. I think they'd help explain this a little bit. Anyway, so we're going through types of bonds. We're doing this 2 strong bonds. Ionic bonds is up first, so let's jump right in. And it says atoms are most stable when their outer electron shell, the valence shell, is full. False. Well, I should say almost true. Atoms want their valence shell to be full, empty, or 8. The first shell can hold a maximum of 2. So it's super happy when you have 2. That's why helium, which has 2 protons, and balancing that out has 2 electrons. Helium is really stable and doesn't react with anything. It's one of what we call the noble gases. It doesn't react because it has a full layer. You're like, oh, look at these electrons I can share with you. Like, yeah, I'm good. I got what I need. Just leave me alone. I'm happy. Everything's good. All right. So inner layer can hold 2. First layer can hold maximum of 2. Second layer can hold maximum of 8. And so far you're like, I don't see the problem, because, you know, full layer, 8 layer, same thing. But here's the deal. You have the next layer out, it can hold a maximum of 18, the third layer. And those atoms literally will be like, okay, I'm adding, I'm up to 8 and it's perfect. And then you try to add another one and they're like, no, that's horrible. I love 8. I will shove that extra one off and get rid of it. And it's something I don't want because I want 8. So they're saying, oh, well, atoms are most stable when they're full. Yeah, no, full, empty, or 8, the outer layer. When I say empty, that's because, say you are lithium and you have 1 in your outer layer, you're in that first period, that first column on the table. What do you nobody wants 1 in the outer layer, so what do? You throw it away because you have a full layer underneath. You get rid of that one because you have a full one underneath. So you could say it's that they wanted that layer that had 1 to be empty, or you could say that they wanted to expose the full layer underneath. Either way, full, empty, or 8. Those would be the 3 things that would make an atom stable or happy. So in an ionic reaction, we create ions, okay? These are atoms with weird numbers of electrons. So atoms that have weird numbers of electrons are ions, and this happens because they're trying to get that outer layer to full, empty, or 8. And what they'll do is either take electrons or shove electrons away to try and get to their ideal number. All right. So it says during an ionic reaction, atoms donate or take on electrons to fill their valence shell. Totally true. This results in the formation of positive or negative ions. Think about why. Say you are stable. Say you have the number that you want. I'm jumping here. Cheating and looking for a periodic table. There we go. All right. Say you are, we'll go real easy. Say you're fluorine and you have an atomic number of 9, okay? That means that you have 2 in the inner, 7 in the outer. You are only 1 away from the happy place, 8 in the outer layer. So what are you going to do? You're going to take an electron to get to 8. I mean, it's a lot easier than trying to give up 7. So you take 1, you get to 8, and you're in the happy place. You've got 8, you're stable, it's all good. But if you started out with 7 protons, sorry, with 9 protons and 9 electrons, and now you have 1 extra one, you have 10 electrons, they were balanced, but now you have extra electrons. These are positive, the protons are positive, the electrons are negative. You've got more electrons. you have a negative charge. Say you start out the same and you're lithium and you have that one extra one you want to get rid of, and you do get rid of it. You lose that electron, you have fewer electrons. Now the protons weigh more, or protons have more charge. They're not balanced, and you are positively charged because you have more protons than you do electrons. So I guess that's what I'm rambling towards. If you have more protons than you do electrons, you are positively charged. If you have more electrons than you do protons, you are negatively charged. So we start out neutral, but atoms that gain or lose electrons, they become ions. But what kind of charge that ion has depends on how many electrons it gains or loses. All right, so let's move on again. All right, so during an ionic reaction, we're going to make ions. Atoms are either going to give up or take electrons, and that will give them a charge, either positive or negative. And if they are positively charged and negatively charged, they're attracted to each other like magnets are, the positive and negative ends of a magnet. So these atoms will be attracted to each other. So here we have an example, the most famous example. It's in every textbook. We have sodium that has 1 in its valence layer. We have chlorine that has 7 in its valence layer. Sodium would really like to get rid of that 1 in the outer layer because look, it has a full layer underneath. It has 8 in that layer. Oh, makes sense. Chlorine would really like to get an extra one because if it had 1 more, it would have a full layer. So we're happy. So sodium's like, I really wish I could get rid of this. And chlorine's like, really? Because I totally want to have it. And so sodium gives the electron to chlorine. And you might say, oh, well, they'd both be happy and move off in their merry way. But no, because the sodium now has a positive charge because it has more protons than electrons. And the chlorine now has a negative charge because it now has more electrons than protons. So what happens? They both have a charge, they are attracted to each other, they stick together. That is an ionic bond. I like to tell people, think of it as the sodium being like, if I could just get rid of this electron, everything in life would be great. And they stick that electron in something else, and they get ready to walk away, but now they have a charge, and they're attracted right back. They're not any further from the electron than they were. All right, let's move on. So ionic bonds, we gained or lost electrons and we became ions. In covalent bonds, okay, so ionic bonds, you gain or lose electrons. Covalent bonds, you share electrons. The things towards 1, towards 7, those periods of the periodic table, they really want to lose electrons or get electrons. The ones that are in the middle, think of carbon. It's got 4 electrons in the valence layer. There is no way it's going to lose 4 or steal 4. That's just too much work. So carbon's like, do you just want to share electrons? And that's what a covalent bond is. They're sharing electrons. A single covalent bond, each atom contributes 1 electron. A double covalent bond, each atom contributes 2 electrons. You could even have a triple bond where each atom has 3 electrons. That's super, super powerful, strong. And we draw those with straight lines. Okay. In reality, what happens is the electrons are going around this one, 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 around this one. They can't move apart anymore. All right. So here we have some covalent bonds. We've got water. Remember, it is H2O. We've got 2 hydrogens. We've got 1 oxygen here. And the 2 hydrogens want to join the 1 oxygen. So each hydrogen has 1 electron in the outer layer, but it wants to get to the happy place. It wants to have the full valence layer, which for them, because they've only got 1 layer, that's going to be 2. how do they get to? They hook up with oxygen. And then oxygen, it has 6, 4 in the outer layer, okay? And it would like to have more than that, okay? So what you end up with is that oxygen, whenever it is bound in a hydrogen, it temporarily has 1, 2, 3, 4, 5, 6, 7, 8, because what's happening is it's got the extra 2 electrons. It has the electron from the hydrogen, the electron from this hydrogen, that adds up to 8, so it's happy. But each one of these is happy, is stable. Each one of the hydrogens is good because it has its original electron plus the one that's being shared. And that gives it 2 in the outer layer. So water, 2 bonds, so water where oxygen has 2 hydrogens bound to it, stable. The oxygen's happy, the hydrogens are happy. Now, we haven't talked about this yet, but oxygen is, it's not all well and perfect and happy like in this drawing. Oxygen is very electronegative. That means it wants to gain electrons, it wants to become negatively charged. It's going to hog those electrons. They're going to spend a little more time around the oxygen than they do around the hydrogens. And that'll make the oxygen end of that molecule a little bit negative and the hydrogen end a little bit positive. And we'll talk later about what that means. Basically, you create a polar covalent bond, where, like a magnet, you have poles. You have a negative pole and you have a positive pole. Now, oxygen, diatomic oxygen, 2 atoms of oxygen joined together, that's another way that oxygen can get its outer layer of 8. And in that, you've got this, and they're the same thing, so there's no poles. Nobody's hogging the electrons more than the other one. This one can't hog the electrons very much because that one wants them. And this one can't hog them much because that one wants them. So they're forced to share. So they're forced to share equally. Anyway, let's move on. All right, so this is a check your progress where you're going to talk about electrons, neutrons, and protons. They want to use magnesium as an example. You can read the instructions. I'm going to pause for a second here. Okay, so see if you can answer these questions. I'll pause for a second and let you do that. If you can't, stop the video, rewind it, go back, watch the last section again. Let's move on to the next section. All right, so we're going to talk about properties of water. And I'm moving this down, sorry about that. In the next section, we are talking about properties of water. Okay, we've got isotopes, probably properties of life. Let's see. Yeah, okay, yep, properties of water, properties of life, we're good. All right. We'll talk about hydrogen bonds. You already know about polar covalent bonds, and we'll build on that when we talk about hydrogen bonds. And we'll talk about the pH scale. The short version, I know this is weird, but you got to remember it. The lower the pH number, the higher the amount of hydrogen in the solution. The lower the number, the higher the pH. Don't blame me. It's not a biologist's fault. This is a chemistry thing. The reason why is because there's a negative number. A pH is a negative logarithm. So the formula has a negative in it, and it flips what you would expect upside down. Just know that the lower the number, the stronger the acid. So like stomach acid, really, really powerful acid, pH 2. Something like coffee, I'm going to guess 6 maybe. Water, pure water, neutral. And then as you start getting more and more basic, the numbers go higher and higher. Like oven cleaner is going to be a a pH of like 12, so super basic. The lower the number, the more acid. All right, move on. So water is the most abundant thing in us. 70% of our total body weight. Water is polar. You already heard that. We already talked about it. Here we're making a water molecule right there at the top, the Mickey Mouse looking thing. We've got 2 hydrogens and 1 oxygen. And so we have a little bit positive and a little bit negative because the oxygen is hogging the electrons. They spend more of their time around the water than they do around the hydrogen. So there's the book saying the same thing. Electrons spend more time around the oxygen than the hydrogens, and that creates a partial negative charge. So what that means is that every water molecule has an oxygen end that's a little negative and a hydrogen end that's a little bit positive, and they line up with the other water molecules. So the negative of this one faces the positives of this one, and the negative of this one faces the positives of that one. Don't worry, the gecko video that I put below has some real nice animations and drawings showing that. So here we have the polarities shown, where we have a little bit positive down here, a little bit negative up there. All right. So hydrogen bonds are attraction between slightly positive hydrogen, slightly negative oxygen or nitrogen, and we draw them with dotted lines. That lets you know that they're weak. If we're using a solid line for a covalent, it's strong. Dot, 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 that's, oh, we're bound, we're not, we're bound, we're not, we're bound, we're not. It's on again, off again. They're weak. All right. And there it is. We got all the waters floating around. And you can see we have dotted lines between them. Dotted line from this positive hydrogen over to that negative oxygen. From this positive hydrogen to that negative oxygen. Great. Now this is important because it takes energy to make and break bonds. Even weak temporary bonds like hydrogen bonds, it takes energy to make and break them. And because all water molecules are involved in these hydrogen bonds, it takes a lot of energy to change water from one state to another. We'll get to that. So hydrogen bonds between water give them special properties. Water is liquid at room temperature, but it has a high heat capacity. That means it takes a lot of heat to change it. 1 calorie is the amount of heat needed to raise 1 cubic centimeter of water, 1 gram of water, 1 degree Celsius. And this prevents big temperature changes in the body. What am I talking about? What I'm saying is that if you want to, say, evaporate the water, if you want to turn the water into a gas, you're going to like heat it up until it boils. You have to put enough heat to break all those hydrogen bonds so the water molecules can escape as a gas. So high heat of vaporization, high heat capacity. Because water has lots of hydrogen bonds, if you want to go from a solid to a liquid, you have to put a lot of heat in because you got to break a lot of bonds. If you want to go from a liquid to a gas, you got to put a lot of heat in because you got to break a lot of bonds. All right. So there we show temperature change and amount of energy. And these vertical lines are kind of cool. Like say you're going from solid to liquid. Here's where it's going to change. All right. And that change, we stay at 0 until it melts. We don't warm up. We stay there until the whole thing melts. Anyway, the big take home here, lots of energy. Lots of energy put into change phases. All right, now water is a solvent, and again, the book's not saying anything particularly wrong. It just has the most unimaginative way of describing solutions and solvents and solutes, and I think there's an easier way. This is how I usually break it out, because everybody knows what Kool-Aid is. So if you want a refreshing Kool-Aid drink, that is a solution, okay? That is a solution, a refreshing Kool-Aid drink. Now it has stuff in it. It has solutes. Those are the things we're dissolving. I'm talking about the Kool-Aid powder and the sugar. Those are solutes. And it has a solvent, water. In biology, water is usually the solvent because water, polar molecule, it's good at dissolving most things. Most things in biology, not the lipids, I know, but most things in biology have a little bit of charge to them. So water is a good solvent for dissolving them, but a solvent is the stuff you dissolve things in. In our refreshing Kool-Aid drink, water is a solvent. The Kool-Aid powder, the sugar, is a solute. And what we make when we dissolve the solute in the solvent is a solution, which is very tasty. Okay, so here we are back at the book PowerPoint. And I want you to know it's not entirely useless. Wow, that's not showing a share. That scares me. I don't know what got shown and what didn't. So we're going to do it this way. You are screen sharing. Okay, that's what I wanted. All right, so when we look at this, it's not entirely useless. It shows hydration shells really, really well. Okay, water's a solvent. It's good at dissolving things. We said that a solution is what happens when we make solute like water and solvent like water, dissolving solute stuff. In this case, the book's talking table salt. But that's not bad because you can see that the way it works. The way that you keep a sodium away from a chloride in solution is that sodium is surrounded by waters. And in those waters, the negative oxygen lines up facing the sodium. And the positive hydrogen lines up facing the negative chlorine. All right, that makes sense. But you form these hydration shells. So this ion and this ion can't get close to each other anymore because they're surrounded by spheres of water, hydration shells. All right. So water is a good solvent. We said that. Polar molecules, things that have charges on them, attract water. And so we would say they are hydrophilic. Hydro meaning water, and philic from the Greek word philos for love. All right. Hydrophobic molecules, those are non-polar molecules. Those are the lipids, say. They don't attract water. And so the overly imaginative word hydrophobic means water fearing. You know, phobia is a fear. So hydrophobic is water fearing. And the water fearing lipids, the things like oils, oil and water don't mix. Yeah, no duh, because the water is polar and the oil is nonpolar. All right. Cohesion is when the water molecules or anything stick to each other, and that's caused by hydrogen bonds. Adhesion is when they stick to other surfaces, like blood vessels or like the walls of the xylem and phloem vessels in trees. You know, that adhesion is caused by hydrogen bonds. The cohesion, it's caused by hydrogen bonds. The hydrophilic and hydrophobic attractions, well, so the hydrophilic attractions that let most biological molecules dissolve, hydrogen bonds. Why water is a good solvent for most things? Well, most things have charges, and so they're good at making hydrogen bonds with the water. The reason it takes so dang much energy to go from a liquid to a gas or from a solid to a liquid, well, it takes so much energy to change water's phase because you got to break a lot of hydrogen bonds. So yeah, all of these properties of water, almost all of these are due to hydrogen bonds. All right, let's do another one. As liquid water cools, it gets less dense. That is weird. That is odd. Almost everything in the world, as it gets cooler, it gets more dense. But on this planet, we got a lot of water. Water does that for a while, but as you get cool enough, it reverses, and then it starts getting lighter. That's why ice floats. Why? Because when you look at it, the liquid water, you have some of the hydrogen bonds. The solid water, the molecules have moved apart until they can maximize their hydrogen bondiness and have all the hydrogen bonds possible. That creates extra space. That's why if water gets into a crack and freezes, it expands and breaks the rock further. But that's why we have water less dense, because it's expanded. That's what makes water float. They have all the hydrogen bonds. So, all right, acids and bases. We already talked about it, but let's talk about it some more. Acids are substances that come apart in water and release hydrogen ions. The more hydrogen ions you have, the more acidic that solution is. So hydrochloric acid, that's a strong acid. It's a fancy way of saying it disassociates, it falls apart fully. Hydrochloric acid, you get it near water, you got a chlorine, you got a hydrogen. It's not like carbonic acid, I might separate or I might not. No, hydrogen, strong acid, you got hydrogen. All right, so moving on. A base is the opposite of an acid. It's something that either takes up hydrogen or releases hydroxide. All right, so here we have sodium hydroxide. It separates into a sodium ion and a hydroxide ion. We haven't talked about these, but there are some atoms that stay hooked together and as a group have a charge. And that's what you're seeing there with the hydroxide. The OH acts like one atom when it moves around, one negatively charged ion. All right, so a pH scale is a measure of how acid or basic something is. The word alkalinity or alkaline, it's the same thing as saying basic. The pH scale ranges from 0, super acid, like melt your face, to 14, ultra super basic. 7 is in the middle. That's when you got a balanced same number of hydroxides and hydrogens. That's neutral. All right. If something is below, so 7 is neutral. If something is below that, we say it is acidic. If something is above 7, we say that it is basic. All right. And the hydrogen ions are what change, how many hydrogen ions you have. And it's a logarithmic scale, so everything is not little numbers, it's huge changes. All right, so here we have a pH scale. All right. They flipped this one upside down, which I don't think helps people, but they did this so the highest location you see, which is pH 0, would have a high acidity, a high number of hydrogen ions. I think it's easier to just remember, if your number is less than 7, you're acidic. If your number is more than 7, you are basic. Moving on. So a buffer is a chemical that resists changes in pH. A good example of that, I've done classes before where we take a test tube of water and a test tube of blood plasma. We pour a little bit of hydrochloric acid in each one. When we do, the pH of the water one, it drops. The pH of the blood plasma, nothing happens. And then we pour more acid in. and the pH goes down in the water and nothing happens to the blood plasma. And we pour in more and the pH of the water drops some more and the blood plasma does nothing. And then we pour again and the pH of the water goes down and boom, the pH of the blood plasma goes down, like way down. Why? Because blood plasma, your blood should always stay at a pH between 7.35, 7.45, average of 7.4. If it doesn't, if it goes above or below 7.35, 7.45, you have problems, big problems. It would be metabolic acidosis, maybe something like that. But the body has to stay in that narrow range. If you pH gets too low, blood doesn't even want to carry oxygen, so it's bad. Anyway, a buffer is something that keeps it in a certain range. And your blood actually has 4 buffering systems. The one we're going to talk about a lot is the bicarbonate buffering system, but there also is the albumin, one of the main blood proteins. It works as a buffer too. If there are too many hydrogens floating around in the solution, it can hold on to them and carry them away. So anyway, it says carbonic acid and bicarbonate are buffers in the blood. That's going to be the main one. They absorb hydrogen and hydroxide from metabolism, and that stops us from having these huge swings of pH being too acidic, too basic, too acidic, too basic. All right, let's move on. Oh, it's a check your progress. I'm gonna be quiet for a few seconds and you can pause the video, look and see if you can answer these. If you can, we'll just move on. If you can't, rewind it and watch the last section. Make sure that you can answer the questions. Okay, now we talk about the 4 classes of organic molecules, big macromolecules. And right off the bat, you've heard of these things. I'm talking about carbohydrates, I'm talking about proteins, talking about lipids, things like fats, and the nucleic acids, the DNA and the RNA. So you know about these things. We're going to list the 4. We're going to talk about how they're assembled and disassembled. Let's do the thing. So carbs, lipids, proteins, nucleic acids, good. Organic molecules contain carbon, hydrogen in large amounts. We think of them as being things we see in cells. Each one of these is composed of subunits. I'll tell you in not so much the lipids, but in the carbs, the proteins, the nucleic acids, we're talking long chains of repeating subunits. And those little subunits were generically, we call a monomer. Like, oh, here's one of them, you know, mono. Here's one, monomer. And the whole chain, if you have many, we say poly, so a polymer, okay? And there are smaller chains, like if you have 2 things, it's a dimer, like table sugar, milk sugar, so yeah, that's made out of a glucose plus something else, I think a lactose. But yeah, you have this plus this, the 2 together are a dimer. And so when we digest them, we break them apart, hydrolyze them. All right, moving on. So, and there we, just what I said by accident. The hydrolyzer, hydrolysis, that's adding water to a molecule to break it into subunits. So say we have 2 things here, they're hooked together. If we shove a water in between them, we can put a hydrogen on this one, an OH on that one. We've broken the water, but more importantly, we've broken the bond between these 2 things as well. That's hydrolysis, okay? I want you to remember the word lyse, L-Y-S-E, that's what this is based on. Because lysing is breaking things. And so hydrolysis means literally to break with water, to break with water. All right. the opposite of that would be a dehydration reaction, or a lot of people say dehydration synthesis. In this, you take this and you take this and you hook them together. How? You pull an OH off one, you pull an H off the other. Now they're attracted to each other, they bond, they share molecules. That is dehydration synthesis. Synthesis because you are making something, and dehydration because you are removing the water from their lives. Which, sorry, from their lives was silly. We'll stay focused. Okay, so dehydration reaction, you remove an OH from one side and H from the other, and those two subunits hook together. An example of this would be like the peptide bond like you have in a protein, the bond between the amino acids. That would be created with dehydration synthesis. It's a dehydration reaction. Moving on, sorry about that. All right, so here we show hydrolysis and dehydration reaction. This is a fabulous drawing. You can see that if we are taking an OH off of one side and H off the other and give it off as a water, these two subunits get hooked together. And the example of that, like I said, is the peptide bond that's created between amino acids as you're building a protein. And here we have the opposite. We are shoving a water into a bond. Two subunits are hooked together right here. We shove water in there, put an H on one side and OH on the other, and boom, you got separate pieces. You got separate pieces. All right, so let's move on. This is 2.3. Again, make sure you can go over this. Make sure you can answer the questions, and then we'll move on. Okay, let's jump into carbohydrates here. So carbohydrates are mostly carbon, hydrogen, and oxygen. You have twice as much hydrogen as you do oxygen. And they are actually, yeah, I'm sure what they meant to say is twice as much hydrogen as you do carbon, because each carbon, they're long chains of carbon, and each carbon has a hydrogen on each side most of the time. So that's a description of the middle of the chain. But yeah, this slide where it says the ratio of hydrogen to oxygen is 2:1. Yeah, they're probably talking carbon to hydrogen. I'm sorry, hydrogen to carbon. All right, but anyway, carbohydrates are energy sources. I'm talking about things like sugars in all their forms. So it could be something like glucose. It could be something more complex like fructose or sucrose. It could be, instead of a sugar, a starch, which is a long branching chain of glucoses. If you had an even more branched, more elaborate one, then you'd have glycogen. Starch is what plants tend to use as an energy storage molecule. Glycogen is what animals tend to use. Anyway, and it says in plants it can be structural. Yeah, they're talking about like cellulose. Anyway, which again is another polymer of glucose, but it's one where things are hooked together like this, and our enzymes are used to going down like this, and if the sugar switches sides, they don't know how to digest it well. We'll get into that. All right, so moving on. Something's made out of one sugar, one. Mono means one. Like a monoplane has one wing, and a biplane has two wings, and a triplane, like the Snoopy and the Red Baron, the Fokker DR3, that had three wings. So anyway, mono for one, and a monosaccharide is a single ring of carbon sugar. All right. Has a carbon backbone, 3 to 7 carbons. Pentose, for example. Pentose has 5, like pentagram. Glucose is the most common monosaccharide. It is the one that we're going to talk about the most in this class because the breakdown of glucose, which is called glycolysis, is the first of the 3 steps. The total breakdown of glucose would be glycolysis, Krebs, and the electron transport chain. That's the main metabolic process we're going to discuss in this class. That's how you get ATP. The glycolysis part, which means the breaking of sugar, it takes the 6-carbon glucose and breaks into 2 3-carbon things that we call pyruvates. But after that, you go through the Krebs cycle in the mitochondria, and you go through the electron transport chain in the mitochondria. Both of those require oxygen. The glycolysis, which happens outside the mitochondria, does not. But we'll get into all that. There'll be a bunch of that. Anyway, glucose is the most common source of glucose is a monosaccharide. It's the most common one. It is the monomers that are used to build starch and glycogen and cellulose, and by itself, glucose is a really good source of energy for us, for the body. Your brain only runs on glucose, for example, most of the time, almost all the time. All right, so here's some pictures of glucose. Yay, different ways they've drawn it. So glucose is a monosaccharide made out of 1 ring of carbon. A disaccharide is made out of 2, all right? Sucrose, table sugar, that is a disaccharide. So is lactose, milk sugar. They're saying here, lactose intolerance results if one can't break down lactose. Yeah, it would probably be better to call that a lack of lactose persistence. I know I'm being nitpicky, but there's a great HHMI video about that. I will add that to the links of things that you should probably watch. If you don't watch it now, you're going to see it. I will make that link available multiple times in this class. It seems appropriate now when we're discussing lactose, but it also would be appropriate when we talk about genetics, and it also would be appropriate when we talk about digestion. So you're going to see that several times. Anyway, hold on a sec. Okay, I just opened up a link to the lactose video from HHMI to remind me to give you guys that link, which you'll see below. All right, let's move on. So disaccharides, monosaccharides. If you take 2 disaccharides and you move them together to make, if you take 2 monosaccharides and put them together to make a disaccharide, that is an example of dehydration synthesis, dehydration reaction. You see it here going left to right. You could also take a disaccharide and break it into 2 monosaccharides. That would be done through hydrolysis. I want you to know dehydration reactions and hydrolysis, or I might say dehydration synthesis and hydrolysis, but you need to know those terms. All right, poly means many. So polysaccharides are made out of many monosaccharides, usually many glucoses. Starch, I already said, is an energy storage molecule in plants made out of lots of glucoses. Glycogen, energy storage molecule in animals, also made out of lots of glycogen. It has a few more branches in it than a starch. Cellulose is a structural polysaccharide. It is difficult to digest. If you look at starch, all the glucoses are lined up the same way, and they're easy to cut off and cut one off, digest, cut one off, digest, cut one off, digest. The glycogen works the same way, arranged the same way. Remove one, metabolize it, remove one, metabolize it. Cellulose, those monosaccharides, those glucoses are this way, this way, this way, this way, this way. Our enzymes don't know how to break that down, so we can't. This is the fiber that we say, oh, it's not digestible, and and it helps clean out your colon, and all true. But it's just because we don't have the enzymes for it. There are organisms that do. There's a little tiny protist called Trichonympha that lives inside the guts of termites. Termites can't digest cellulose either. You think, oh, well, they eat wood all the time. Yeah, they can't digest the cellulose, but they can chew it up in tiny, tiny, tiny pieces that are then eaten by the Trichonympha living inside them, and the Trichonympha break it down with their special enzymes until you have glucose, which they share with their host, the termite. Let's move on. All right, so here we have pictures, non-branched versus branched. So yeah, so we're talking starches. And here you can see the much heavier amount of branching that we have in the glycogen. That would be the animal protein. And here you see cellulose, how you like, oh, well, those are simple in a chain. Yeah, but look where the oxygens are. They're on opposite sides. Those are not lined up in the same way, and our enzymes can't flip around. All right, here is another check your progress, 2.4. So look over the questions, make sure you can answer them. I'm going to pause for a second so you can stop the video and do that. If you can't answer them, rewind the video a little bit, go back to the last progress check, and watch this segment again. And now let's move on. All right, we talked about carbohydrates. Let's now talk about lipids. I'm talking about things like oils, fats, the phospholipids that make up your membranes. I'm also talking about steroids. They're made out of sterols. Sterols are lipids that have ring shape. They have like rings of carbon in them. And your steroid hormones are made out of sterols. So are things like cholesterol. So are things like, well, testosterone. So anyway, we'll talk about what the different things do. And of those, my favorite are the phospholipids. Yes, I have a favorite lipid molecule, and it is phospholipids. But let's move on. All right, so lipids don't dissolve well in water. That makes sense. You know, oil and water don't mix. That's what we're talking about. Why do they not mix? Because the water is polar and the lipids are non-polar. They don't like that. They don't have charges, so they don't stick to the charged water molecules very well. In general, in chemistry, there's a phrase they use a lot: like dissolves like. Like dissolves like. So water, because it's polar, because it has charges on the molecules, is good at dissolving most biological molecules because they have charges on them. Most lipids do not have charges, they are not polar, and therefore they're not going to dissolve well in water. The exception is the phospholipid, which is incredibly weird because it has an end that loves water and an end that hates water. So it has a hydrophilic end and a water-hating hydrophobic end. We'll talk a little bit about these as we move on. We're going to talk about trans fats. We're going to talk about triglycerides. That means it has 3 fatty acid chains attached to a glycerol. Anyway, let's move on. Oh, well, right there, a triglyceride is made of 1 glycerol and 3 fatty acid chains sticking to it. These are like common in animal fats, and they're good at energy storage. They're good at insulation. Think of that nice blubber layer on a whale or a seal. They're good at cushioning. I'm talking about the fact that one of your kidneys hangs partway below the rib cage. It's not protected by the rib cage, but it has a nice capsule of fat around it to, if someone's uppercutting you, it will absorb some of that impact and prevent you from getting really smashed up as badly in the kidneys. There are 2 main fats of two main forms of triglycerides: fats and oils. Fats are usually animal-based. Usually, coconut oil is an coconut is an exception. Coconut is a saturated fat, kind of like animal fats. Fats tend to be solid at room temperature. The reason why is these tend to be saturated fats with long, straight chains, and that lets them pack together closely. So 1 teaspoon of that animal fat has many, 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 many molecules of fat. And so they're solid because they're packed tight together, can't move past each other easily. Oils tend to be plant-based in origin and liquid at room temperature because they tend to be unsaturated, maybe even polyunsaturated. That means that there are places in the fatty acid chains that don't have as many hydrogens. And what that does is it allows bends and kinks in the fatty acid chain, which makes each molecule bigger, thicker, which means you can't pack as many of them close together, which means that they're more liquid at room temperature. All right, so let's move on. So here we have fatty acid. There's 3 fatty acid chains and a glycerol joined together to form a triglyceride. And in this case, these are both, these two are saturated. You can see they have all the hydrogens they could hold. This one here, it is unsaturated because right there's a double bond. Now remember, every carbon wants to have 4 bonds. They always want to have 4 bonds. So let's look at this one here. And this carbon has 1 bond to a carbon, 1 to a hydrogen, 1 to a carbon, 1 to a hydrogen. It's happy because it has 4 bonds. Well, this one has a bond to a carbon, another bond to that carbon, a bond to the hydrogen, a bond to this carbon. It's still got 4 bonds. It's still happy. But the thing is, this double bond is special because if you have hydrogens here and not here, the whole chain is going to bend right there as the hydrogens at the top, their electron clouds try to expand, try to spread out, and there's nothing on the other side to stop them, so you get a bend. All right, so enough rambling. What I'm getting at is this triglyceride has a saturated fatty acid, and unsaturated fatty acid. If you hear something is an unsaturated fat, that means you got double or triple bonds in the chain and it is not saturated with hydrogen. It has less hydrogen than it could. All right, so triglycerides are hydrophobic. They don't like water. They clump together in body fluids. We have little droplets that are forming. So those emulsifiers and molecules that surround triglycerides disperse or emulsify, and that means break them into tinier droplets. We do this because it increases the surface area. If you have a bunch of little droplets instead of one big droplet, there's a lot more surface area for the enzymes to work on. And it's not saying it here, but I'll tell you, the main emulsifier in our digestive system that I'm aware of anyway is bile. So the liver makes bile and it's stored in the gallbladder. And if you have a big fatty meal, when that food comes into the small intestine, the duodenum, the gallbladder is going to squeeze and squirt bile into the duodenum, into the first part of the small intestine, to emulsify the fat, to take big drops of fat and break them up into tiny little droplets with lots of surface area so the enzymes can chew on them. All right, so we talked about that. Let's talk about waxes. This is one fatty acid attached to an alcohol. And waxes, like on skin, they can prevent the loss of moisture. A good example, that would be your earwax, which the fancy anatomy word for that is cerumen. All right, let's move on. Oh, let me click here. Now let's move on. All right, so now we're going to talk about saturated fats, unsaturated fats, and trans fats. Fatty acids are long chains of carbon and hydrogen that end in carbon, oxygen, oxygen, hydrogen. Most of them have 16 to 18 carbons long. They can be saturated or unsaturated. I will let you know that the further down in the ocean you go, the more unsaturated the fatty acid chains tend to be in the phospholipids. But we'll talk about phospholipids later. But it prevents the close packing. Remember, if fats are saturated, they pack together real close. All right. So saturated fats are saturated with hydrogen. They got all the hydrogen they can have, and that means there are no double bonds, double covalent bonds between the carbons. You already saw from this picture, if you have a double bond, you're missing some hydrogens you could be holding. So here, saturated fatty acid, here, unsaturated fatty acid. Moving on. All right, unsaturated fats have one or more double covalent bonds, and that causes hydrogens to go missing. Now, polyunsaturated would mean you have many of those double or triple bonds. These unsaturated fats, they tend to be liquid for reasons I already told you. You can't pack them as tight together. Anyway, those bends make them further apart. Now, comparison of saturated, unsaturated, and trans. So here we have a saturated fat, and that'd be like butter. And here we have two unsaturateds. This is an unsaturated because it has less hydrogen than it could. It's got a double bond there. This would be also be called a cis fat. Cis, things are on the same side. The sound of cis, even though it's written CIS, the sound of cis, it sounds like same. And so things tend to be on the same side. Here, we have trans. Trans means across or away from. If you think about it, if you transmit, you're sending something out. If you drive from one side of the country to the other, you're going on a transatlantic highway. If you fly from one country to another over the ocean, so you're going over the Atlantic and go see Europe, it'll be totally cool. It is a transatlantic flight. Trans, things are on the opposite side. They're drawing this with the hydrogen, but the R group side chains would be too. Trans fats they're real uncommon in nature, and we're not real good at digesting them. So we tend to make some mildly toxic byproducts when we try. Anyway, that's why when you hear something is partially hydrogenated, what that means is they took an unsaturated fat and they put it under high heat with an atmosphere of hydrogens, literally trying to break some of the double bonds and stick a few extra hydrogens on. When that happens, some of these go in the normal, natural way, which is cis, and some of those go in that weird trans direction that you don't really see that often in nature, and we're not that good at digesting. All right, so saturated fats can contribute to hardening of the arteries, so disease of the blood vessels. Trans fats tend to not be natural, they're man-made, and they tend to do other bad things to heart disease. They're unsaturated, but the missing parts are on opposite sides. All right, back in the day, they used to say you shouldn't have more than 65 grams of fat in a 2,000 calorie diet. Now they say the type of fat is way more important than the amount of fat. Here's the food label, and it looks at the different types of fat. This, whatever they're eating, it has 12 grams of fat, and 1.5 of those grams are trans fats. But fats, cholesterol, sodium, those are things that we should try and steer clear of if we can. Vitamins, calcium, iron, those are things we probably need to get. Moving on. Okay, now we're talking phospholipids. Phospholipids are way cool. All right, phospholipids are Molecules that have the opposite ends act opposite ways. Hold on. Okay, much better illustration. You can see here that phospholipids are a little bit like cat dog. We got one end that loves water, that'd be the head, and one end that hates water, that'd be the tail. Okay, so hydrophilic head, hydrophobic tail. The reason why is simple. The head, remember we said before, oh, lipids have no charge on them. Not true of phospholipids. The head of a phospholipid has pretend to be shocked here, a phosphate in it. And the phosphate has a charge because you got oxygen, 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 and they're very electronegative. They're sucking all the electrons in there. There tends to be a negative charge right here. And what that means is that the tail, which is water hating because it's nonpolar, is the exact opposite of the head, which has a charge because of all those oxygens. All right. So what you're going to have happen is the molecules are going to line up with the heads, which like water, towards the water. Then you got water outside the cell, and you got water inside the cell. What that means is that you're going to form a layer of phospholipids with the heads lined up towards the water on the outside. But that's not it, because those molecules really hate water. So the ones that are on the inside, they're going to line up with their heads towards the water and their tails away from the water. What that means is you're going to get this bilayer, this double layer of phospholipids, where you have heads towards the water on the inside, heads towards the water on the outside, and in between, tails, 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 all the water-hating tails. Now, that's what the main component of a membrane is, a cell membrane. It's a phospholipid bilayer, a double layer. And this is basically what keeps the things inside the cell in and the things outside the cell out. Now, there's cholesterol, there are proteins, there are other things in that membrane, and we'll talk about that later. But I want you to understand that phospholipids are totally cool. They are a molecule that on one end loves water, one end hates water. And so they line up in a double layer with the heads facing the water and the tails facing away. All right, moving on. Hold on, I'm going to go back to, instead of my PowerPoint, for my other class, I'm going to go back to the PowerPoint for yours. I just like that cat dog illustration. Okay, so we're back on yours. You understand that a phospholipid has two tails, not three. It has the head being a polar, a charged phosphate. That water-loving head, water-hating tail. They're going to cause you to form a bilayer. Heads towards the water, tails against the water. And, sorry, heads towards the water, tails away from the water. That means the tails point towards the inside of the membrane. And let's move on. All right, there's a picture. You can see a phospholipid bilayer. As you could probably guess, if you are a molecule or an ion and you want to cross this membrane, how well you do it depends on what you look like, what you are. If you are a big charged molecule that brings a lot of water with it, you're probably not going to get across here, because this layer in the middle, this double layer in the middle of all tails, they don't want your water. They're going to push you out. Now, if you are a steroid hormone, you're made out of lipids. You look like this. You're water hating. You'll just zip right through the membrane. But a different kind of hormone, one that's protein based, one that has charges and attracts water, talking about something like insulin, it's not going to get across that membrane very well. You're going to have a second messenger system. That's a fancy way to say you got another molecule on the surface of the membrane, and you may not be able to get across the membrane, but you can give that message to the receptor on this part of the host, part of the membrane, and that receptor will pass on it'll make things happen inside. It'll send a message in for you. It won't let you in to give the message, but it'll send a message for you. The most common second messenger system is cyclic AMP, but we'll talk about that. All right, so steroids are lipids, normal lipids, water disliking, water hating lipids, water fearing, hydrophobic, made out of 4 rings of carbon. All right. And what you have attached to those rings determines what type of steroid you are, or sterol you are. Some are steroid hormones, some are things like cholesterol. Cholesterol is modified and turned into some pretty important hormones like estrogen and testosterone. All right, so there's the example. We've got cholesterol, and you can see you cut some pieces off, you add some other things on. Now you have an important gender hormone, sex hormone. In reality, that's the way we think of those things, but it's not accurate because everybody makes a little bit of the estrogens. Everybody makes a little bit of the androgens. The difference is that men make much more of those androgens and women make much more of those estrogens, but both groups of people make both kinds. All right, let's move on. Oh, there's a progress check. So you're going to pause the video. You're going to see if you can answer the questions. If not, you roll it back, watch the last segment, try again. I'm going to pause a second and then we'll continue on. All right, let's do this. So we talked about lipids, we talked about carbohydrates, now we're going to do the proteins. So proteins are made of amino acids, and the bonds between the amino acids are called peptide bonds. Then we're going to talk about the 4 levels of protein structure and how to denature a protein. I actually have a video about that I should give you a link to. Hold on a second, and I will do that. Now I'll move on, I'll do it later. Okay, so let's jump into proteins here. All right, there's some proteins that your body uses for defense. Antibodies would be an example. They're part of your body's defense. Antibodies are used to detect and disable things called antigens. That's anything that may not belong and that can generate an immune response. All right, it says proteins, there are examples of them that are hormones. Totally true, insulin's an example. But I want you to understand not all hormones are proteins. Don't get confused by the way the slide is written. We already talked about the fact that testosterone, estrogen, made out of cholesterol, made out of sterols. All right. And protein function, we have contractile proteins. I'm talking about the actin and the myosin, how the myosin heads pull on the actin fibers, and that causes the whole muscle to get shorter and thicker. All right, moving on. So proteins are made of amino acids. Amino acids are the monomers that make up the polymer that we call a protein. Every amino acid has an amino group. Pretend to be shocked by that. A carboxyl group, and then R. And the different things that could be R is just a generic placeholder for, oh, and there's a thing here. It could be a really small chain. It could be something really big and huge. But the difference in the R groups is what makes the difference in the amino acids, because they all have an amine and they all have a carboxyl. So, all right, here are some examples. And let's see, let me move that. Yeah, okay, so you can see right here, there's some amino acids that are polar and some that are non-polar. That's what I was hoping that diagram was showing. This is important because The polar molecules want to be near water, and the nonpolar want to be away from water. This is important because things like transmembrane proteins, proteins that go across the membrane, they're going to have an end that has a lot of amino acids that are polar, an end on the other side, a lot of amino acids are polar, and then in the middle, a lot of amino acids are nonpolar. What this means is that protein, even if you don't anchor it inside the membrane and fasten it there, tie it down, it's going to stay, because if it starts to float a little bit up, also it's like, ooh, the middle part that hates water doesn't want to get near the water. If it tries to float down, same things to happen. It's going to move back to where that middle is protected from the water. That middle of that transmembrane protein wants to stay with the fatty acid tails of the phospholipids. All right, anyway, let's move on. So a peptide bond is the bond between two amino acids. This is made with, pretend to be shocked, dehydration synthesis. And if you have multiple peptide bonds, we call the thing you make a polypeptide. Basically, a protein is a polypeptide that is then folded up into cool shapes. But I know this is a little annoying, like when we talked about a polysaccharide, it was named after the sugars. The name means many sugars. Polypeptide, you would think they should call it polyamino acid, but instead they named it not after the amino acids, but after the bonds between the amino acids. Kind of stupid, not my fault. Blame the biochemists. All right, moving on. So you can synthesize or break down a protein. Guess what? We use the same methods we were talking about before. Hydrolysis or dehydration reactions. Hydrolysis or dehydration synthesis. So you need to know that if you take a if you take a water and you shove it into that bond between amino acids, and the hydrogen goes onto one amino acid and the hydroxide goes on to the other amino acid, now there's no bond and they float apart. What you just did was hydrolysis. You lysed or broke the bond using water. All right, proteins have a 3D shape. I've got a link below to one video on protein structure, and I'm going to be adding another one. But understand the 3D shape is super important for a protein function. If you change the shape, it doesn't do its job anymore. And I'll be more specific. If you change a protein from its natural shape, we say you have denatured it. It's no longer in the natural way it was. If you denature it, it probably doesn't work. It stops working. And you can denature a protein by putting it in something that is the wrong pH or the wrong salt concentration, or exposing it to extreme heat. Because when you heat it up, you're going to break the bonds and it will unwind, and that's a change of shape, and then it doesn't work anymore. All right, so proteins. It says all proteins have primary, secondary, and tertiary structure. Only a few have quaternary. So primary is what amino acids you're using in what order. Just the chain, the polypeptide chain, which amino acids, what order they are, that's the primary structure. The secondary is local folding, and that's usually caused by hydrogen bonds. I'm talking about an alpha helix, that's like a spiral, or a beta pleated sheet. That's where you have a whole sheet that the one chain goes down, 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 folding back and forth. And then it bends and it comes back on itself, folding right along with it, folds again, you bend, come back again. That's a beta pleated sheet. But this part that is attached to the other end of the same chain by lots of hydrogen bonds. When you do the alpha helix, the spiral, you can't tighten it because you'd have to break a lot of hydrogen bonds. You can't loosen it because you have to break a lot of hydrogen bonds. I'm not saying it can't be done. If you apply enough heat, like cooking an egg, you can break all those hydrogen bonds. But those hydrogen bonds make it resistant to change. And those hydrogen bonds make the secondary structure. The tertiary structure is going to be like side chain interactions, like say disulfide bridges. Those are covalent bonds. They're stronger than the hydrogen bonds, but not so strong that you can't break them with heat or cooking or other conditions. So here we have a primary structure. It's the sequence of amino acids. What amino acids we use, what order they're in. Great. Then we have a secondary structure. There's the alpha helix. There's the beta pleated sheet. You can see what I said, that breaking is like tightening the spiral or loosening the spiral. You have to break a bunch of hydrogen bonds. Taking the sheet and spreading it or shrinking it together, you got to break hydrogen bonds. So those do your secondary structure. Your tertiary structure is the 3D shape of the whole polypeptide chain. And this isn't just the hydrogen bonds that do the secondary. This also has covalent bonds like I talked about for the disulfide bridges. It also has ionic bonds involved. That's your 3D shape. That's your tertiary structure. If a protein is made out of more than one polypeptide chain, so you have several polypeptide chains, that's when we would call it quaternary structure. And the quaternary structure is the overall 3D shape of the protein, taking into account all of the polypeptide chains. All right, so here we have an example. A tertiary structure, you can see here we have an alpha helix, which you saw in the last picture. Here we have an alpha helix, here we have an alpha helix. But the difference between this one and this one, the angle that those two are at, because they're obviously part of the same long protein chain, polypeptide chain, and they're even close together. But this alpha helix, they're not a continuation. There's a spot here where you could have a bend, but you probably have a disulfide bridge right here, okay? Disulfide bridge right here. Those side chain interactions, that's what disulfide bridges are. They hold this alpha helix and the angle of this alpha helix, and they keep it there. So the hydrogen bonds made the alpha helix. The tertiary structure, the shape of the overall thing, not just this local spot and this local spot, that's caused by disulfide bridges. Great. So tertiary structure, we're dealing with covalent bonds and hydrogen bonds, even ionic bonds occasionally, but they're building the 3D shape of that whole polypeptide chain. And most proteins, that's it. But some other ones, you have more than one protein chain, and those we would say have quaternary structure. Hey, we're done with proteins, and that means we've got a memory check here. Check your progress. Try to answer these questions, and then we're going to move on. All right, let's do this. Now we save the best for last, talking about the DNA. All right. And by the way, DNA is deoxyribonucleic acid, and yes, I want you to be able to spell it. So we'll talk about the differences between DNA and RNA. Let's do that real quick. DNA, almost all the time. I'm going to give you the always true, and then I'll give you the most of the time true, which the book is going to act like is also an always true, but it's not. Okay, so this is always true. DNA, and what these have, both these molecules, they're in a nucleus and they have genetic information. The genetic code is the order that they are in. And DNA, the twisty ladder, it has each side of the ladder, each rail of the ladder has sugar, phosphate, sugar, phosphate, sugar, phosphate, sugar, phosphate. And that sugar is deoxyribose. Now, RNA, it's usually one strand, and it's still sugar, phosphate, sugar, phosphate, sugar, phosphate, sugar, phosphate. And the sugars are ribose. So the first difference I want to focus on is which sugar. DNA always uses deoxyribose, where RNA always uses ribose. That's an always thing. Now, another difference between the two is that DNA uses these 4 bases: adenine, cytosine, guanine, and thymine. RNA uses these 4 bases: adenine, cytosine, guanine, and uracil. So both of them will use an adenine, both will use a cytosine, both will use a guanine, but that 4th one is always different. Uracil is always RNA, never DNA. Thymine is always DNA, never uracil. Okay, so always difference. Which sugar? Always difference. Which base? Now a most of the time difference, but most books treat like it's always. How many strands these have? DNA is usually, almost always, 2 strands. And RNA is usually, almost always, 1 strand. Are there exceptions? Oh, yes, there are. And you have some in your body right now that are called siRNA. It is a double-stranded RNA. But let's move on. Anyway, and then we're going to talk about ATP. Why? Well, you remember we said that both of those use adenine. Well, adenine with some phosphate shoved onto it is ATP, the main energy to run a cell. But we'll get to it. All right, so nucleic acids are polymers of nucleotides. Let me translate. Nucleic acids are long chains, polymers, and their monomers, their individual pieces they're made out of, are called nucleotides. Just like a long cellulose polymer is made out of individual glucoses, a long RNA is made out of little individual nucleotides. Now, each nucleotide is a sugar, a phosphate, and a base. It's a 5-carbon sugar. You already know DNA uses deoxyribose. RNA uses ribose. You already know that they all have a phosphate. And you already know that the nitrogenous bases for DNA are adenine, cytosine, guanine, and thymine. The ones for RNA are adenine, cytosine, guanine, and uracil. Uracil is only an RNA thing. All right, so what's the purpose of these? You can store information. What nucleotide and base you're using and what order they're in. We will explain later what the genetic code is, that code, but that's the code. Just like what letters you use and what order they are in, that tells you what the word is and what it means. What nucleotides you use and what order they're in, that tells you what amino acids you're going to use when you make a protein. All right, so it stores information, instructions for everything that matters, and these are used for chemical reactions. Great. Okay, so you can see each nucleotide is a sugar, a phosphate, and a base. And deoxyribonucleic acid is missing an oxygen. Ribonucleic acid has an oxygen. All right, and they just have C, the nitrogen-containing base. Well, you already know what the bases could be. So let's move on. Deoxyribonucleic acid is DNA. Has information on how to copy itself. What it's telling you is what order that amino acids should be what the order of the nucleotides tells you what amino acids to use and in what order to put them. Now, ribonucleic acid, RNA, some of it's the same and some of it's different. There are different types of it. rRNA helps make ribosomes, the little protein makers. tRNA, transfer RNA, those are like helper chefs that go and get ingredients, bring amino acids to the ribosome. siRNA, small interfering, it helps you shut down things in a hurry if you want to stop making a protein, say. mRNA, messenger RNA, this is like recipes. They have the instructions how to make a protein. You might say, what? I just said that about DNA. Yeah, I did. Let me throw up a link for you, and you watch the beginning of it. It's you don't have to watch the whole video. It's a Nova thing, but it's a really good analogy. They talk about ribosomes as being like chefs, and they read a recipe that's a messenger RNA, and whatever it says to make, they cook it, they make it. So ribosomes follow the instructions. Well, let me start from the beginning. The nucleus has the special recipe book that will not leave the nucleus. You're not allowed to take it out. That's DNA. But you can copy recipes out of it into RNA and throw them out the window, which was the nuclear pore. And then those recipes, those messenger RNAs, they get read on the outside by ribosomes, who follow the recipes and make proteins. All right, so there's the analogy, but I'll throw up a link to do it. Hold on. Okay, I have pulled up the link, so I'll remember to paste it down below so you can look at it. It is the Nova RNAi video. You don't need to watch the whole thing. I usually go right up until they start talking about petunias and colors of petunias, and then I stop. I mean, it's good to watch the whole thing if you're interested, but just understanding how you make a protein, what the role of DNA is, what the role of RNA is, what the role of a ribosome is, that little beginning section where they have the cartoon with the chefs, that's it. If you get up to where you see pirates, you're too far. Okay. Yeah, I know that sounded weird. It's still true. All right. So DNA is deoxyribonucleic acid. I already told you it tells you what amino acids to use in what order. So do some of the RNAs, the messenger RNAs. They are messages because they contain the recipe how to make a protein. And some RNAs are coenzymes that help control enzymes, control whether they work or not. One example of that would be the ATP, okay? Adenosine triphosphate, which you have this phosphate, which is negatively charged, you know, just like a phospholipid. And then you got another one that's negatively charged. And they don't really want to hang out, but you shove them together so hard you make them stick. And then you have another one, triphosphate. You got 3 phosphates, and you shove them all together so close they have to bond. They don't like that. It's like you're taking a bunch of negative magnets and sticking them together. That last magnet, it wants to jump off so badly. That's what's happening here. ATP, it takes a lot of energy to take an ADP and an extra phosphate and smash them together to make an ATP. And you can release that energy when they break off. All right, so let's move on. Here's a pretty little chart talking about the difference between DNA and RNA, which you need to know. The only thing I'm going to add here and change is where they say strands and DNA double-stranded. I'd say double-stranded most of the time. Like in viruses, all bets are off. They do whatever they want. They're double-stranded DNA, double-stranded RNA, single-stranded DNA, single-stranded RNA, antisense DNA, which is DNA written backwards. So yeah, this is a most of the time thing. Moving on. So the backbone of DNA and RNA, I already told you, sugar phosphate, sugar phosphate, sugar phosphate, sugar phosphate. The difference is in DNA, it's a deoxyribose sugar. In RNA, it is a ribose sugar. So here we have a strand of DNA. Yeah, I know we just said DNA is usually 2 strands. Let's talk about one. So we have sugar phosphate, sugar phosphate, sugar phosphate, sugar phosphate, sugar phosphate. Then we have another strand. And that one's sugar phosphate, sugar phosphate, sugar phosphate, sugar phosphate. Between them, I keep comparing the DNA to a ladder. Well, the rungs of the ladder are made out of bases. And if this one has an A or a G, those are the ones that have 2 carbon rings. The other one will have a 1-carbon ring. Adenine always goes to thymine, and guanine always goes to cytosine. But so you always have 3 carbon rings across on each rung. That, by the way, was the big breakthrough in the structure of DNA. The guys who got the Nobel Prize, they weren't the ones who figured it out. It was someone named Rosalind Franklin. She took a really famous photograph. It's called X-ray crystallography. She took a photo of the crystal of the DNA, and it showed that, so here's the twisty ladder. She was looking down at, and she showed that it wasn't lumpy like this. It was always the same diameter all the way down. The only way to do that is to get 3 rings across on every rung of the ladder. Anyway, and then she was cheated out of the Nobel Prize, which we can talk about that some other time. It's a horrible travesty, and the people responsible are bad people. Moving on, just the truth. So nucleotides are usually, we only talk about the base. So we talk about adenine, cytosine, guanine, thymine, or if in RNA, adenine, cytosine, guanine, uracil. Okay, because the sugar and the phosphate are the same all the way down this strand. Whatever the strand is made of for sugars, it's that way all the way down. You don't mix, well, some DNA, some RNA, some DNA, some RNA. Nope, the strand is made of all the same stuff. All right, so DNA is double-stranded most of the time. Okay, the 2 strands twist around each other. Like I said, it's the twisty ladder. They're held together by hydrogen bonds between the sides. Super important. Later on, we might talk about a technique called polymerase chain reaction that requires heating it up until it vibrates and you break the hydrogen bonds, but not enough to break the covalent bonds down the strand. Very difficult, takes very precise temperature control. But we'll talk about that later. And you already heard, adenine is always going to bind to thymine, cytosine is always going to bind to guanine. So that means that on this strand, if you have a cytosine, on the other one you have a guanine. On this strand, if you have a guanine, on this one you have a cytosine. On this strand, if you have an adenine, on this strand you have a thymine. On this strand, if you have a thymine, on this strand you have an adenine. Are we good? Oh, well, that really works well with my black watch and my red I was screened for COVID today bracelet. Anyway, so here's a comparison of the DNA and the RNA, and you can see the differences. You can see they lined them up so you can see the way they bond. This is great. This is peachy. Hey, what are the sugars here in the RNA? They are ribonucleic. It's ribonucleic acid, so they are riboses. What are the sugars here in the DNA? That's a deoxyribose. All right, let's move on. So ATP is an energy-carrying molecule, and it's got 3 phosphates that don't want to be friends, don't want to hang out because they all have the same charge. And breaking the bond between the second one and the third one releases energy that can drive other chemical reactions. That could be making polymers, that could be muscle contracting, nerve conduction, all these things. When ATP breaks apart, you get ADP, adenosine diphosphate, and a free phosphate. And if you put some energy into it, you can stick that back on and make an ATP again. All right. Here we have a picture. We have adenosine and a triphosphate, and dehydration synthesis puts them together. Hydrolysis splits them apart. You've got a free phosphate and the energy that comes from stripping that phosphate off. And you have an ADP you can stick stuff back on, but we already said all that. All right, 2.7 is a check your progress. I'm going to stop now because this is the end. If you can't answer these questions, go back to the last check your progress and rewatch that section. I will talk to you guys again soon.